Hi everyone. Welcome to the second video of Math 2011, 12, and 14 on differential operators. And then I'm gonna continue where I left on the previous video. Now, here, note that we're doing the operators. Okay. Now in this part here, we're gonna say from the theory of linear operators, we can break an equation of higher order into two parts. Higher order can be any order as long as you take it as a higher order. So, but the idea behind this is that we are to break this equation into two parts. So the first part, which is represented as y naught, is the complementary solution, and then the second part, represented as y1, is the particular solution. Okay. Now the general solution of such an equation with higher order is the sum of these two. So the general solution, represented as y, is equals to y naught plus y1. Okay. Now the way we determine y naught and y1 are different because why not when we are differentiating y naught, we equate our operator to 0, meaning that it's that value which is in the null space. Okay. And then going forth, say we have an operator which is linear. Say we have operator PD is equals to d to the minus alpha. Okay. Say that our operator is given this way, and if we want to determine the complementary solution of this, which is y naught, so let this operator operate on y naught. So if we want to find should be y naught. If we want to find the complementary solution of this, we are going to equate this here to 0, and as equating this to 0, it makes this y here 0. I mean y here, it makes y to go to y naught. It's a complementary function. We equate our operator to 0. Okay. Now to work out this, the general formula is d minus alpha y naught is equals to 0. Okay. Solving this from the definitions, which I won't try to prove. From the definition, y naught is equals to a e to the power of alpha t, given that this t here is it depends. D is in terms of what? Say having t here means that we have d dt, which is equals to d. If we had d dx is equals to d, then here it would have been x, not t. So but because I'm willing to work with t, I'm getting rid of this one and then use t. Okay. Now that was the first part. Okay. Now, the second part is when PD is squared. For what I'm saying is, this is the case I'm talking about, is when PD is equals to D minus alpha, okay, and then D minus beta. Okay. Now, given that alpha equals not beta, the solution of these, the particular solution, not just the solution, not particular, complementary, I'm sorry about saying particular, but the complementary solution which we get by equating this to 0, why not, we are going to use the same thing as this part here. Note that A here is just an arbitrary constant. A can be any value, but when we have initial conditions, that's when we can determine the value of A. I'm gonna do a problem where we will have to find the value of A, but for now let's just take A excuse me, let's just take A as an arbitrary constant. Okay. Now, when we want to find the complementary solution of this operator here, this is equals to A e to the power of alpha t plus B. Note that, remember, this is not beta, this is B. I'm saying these are arbitrary constants. Okay. B e to the power of beta t. Okay. Now, there's one thing you should know. It does not necessarily have to be A, B, C, D, E, F, whatever. Okay. It has to be any constant such that the one which is here is not the same as the one which is here. What I'm saying is that we can have A1 here or A0, and then here we may have A1, and then the next one we may have A2, and so on, as long as you specify that these A's here are not the same, then you are doing the right thing. Okay. And now, so what we can see here is that as long as our roots are not the same, then we can have something like say, let me make something general here. I'm just gonna work here. Let me make something general here. Say we have PD is equals to D minus alpha, D minus beta, D minus lambda, and then some other D's up to D minus whatever. As long as our roots, as long as alpha equals not beta, and beta equals not lambda, and lambda equals not whatever that follows here. Now, what we can say now that the complementary solution of this thing here, why not, is giving us A e to the power of alpha t plus B e to the power of beta t plus C e to the power of lambda t plus whatever follows. Now this note that this part is when the roots are not the same. Now I'm going to do the part when the roots are the same. Okay. And I'm asking you to please take note of this, because it is very very important. Okay, let me go to the next page. Okay, now let's say we are given an operator PD is equals to say d minus alpha to the power of k, where k equals not 1. Okay, this condition is very important. This condition here is very important because it's the one which tells us which approach to sort out the complementary solution of an operator. So say that k equals not 1. Now the solution of the complementary the complementary solution of this operator here is given as y naught is equals to a constant plus at plus at squared plus 1 2 3 whatever follows whatever until, note that this must be a, and then the next one must be a2, the next one must be a3. Remember that this should be different. Okay, this should be different. This is a1, take this a1, and this a2, and this a3. They must be different, this coefficients. Okay, and then we're gonna stop at the power which is 1 less than k, and that is a to the let me call that k, let me say k minus 1 t to the power of k minus 1, and then we close the bracket, and then we multiply this here, this polynomial here, we multiply it by e to the power of alpha t. Okay, now with this thing here, you need to take note of something. One thing is that we stop the highest power of the polynomial here is like 1 is 1 less than the highest power of the raised from the raised bracket in this structure. Like we stop at the power of 2 must be less than that, that's why I said k minus 1. Okay, now this is the general form of how we determine y naught. Okay, and then yeah, that was it. On the next video I'll be working out how we determine the particular solution, which is very long. Yeah, and then yeah, that was it for this video. Enjoy the rest of your day. Cheers.